So what are these intermolecular forces? The strength, how strong they are, depends on the structure of the particles, depends on what kind of particles you have. Mentioned before, the state of matter depends on the strength of molecular forces. So if you have strong forces, you're going to have high melting points, high boiling points. It takes a lot of movement, a lot of thermal energy before those molecules can wiggle away from each other. If the forces are weak between the molecules, you have low melting and boiling points. The intermolecular forces arise from interactions between charges. So we can have actual ionic charges, or we could have partial charges from dipoles. We can also have temporary charges on particles. So all these intermolecular forces are electrostatic forces. They're between opposite charges. So let's review Coulombs Law. So the energy, the potential energy of two oppositely charged particles is going to be equal to 1 over 4 pi epsilon naught times Q1, Q2 over R. That looks a little scary, perhaps. Let's just think of it this way. The energy is proportional to Q1 times Q2 over R. This part at the beginning, that's just a constant, a proportionality constant, and we don't need to worry about what that is. Q1 is the charge on one particle, Q2 is the charge on the other particle. In order for this to be an attractive energy, attracting the two things together, the charges have to be opposite. That would make E negative. Negative energy means you're lowering the energy that's going to be more stable. So if the charges are greater, if you have, say, +2 and -2 versus +1 and -1, the energy is going to be greater because 2 times 2 is 4, 1 times 1 is 1. So we predict that the energy would be 4 times as great if the charge doubled on both of them. And then it's inversely proportional to R, the distance between the charges. So the farther apart the charges are, the less attraction there is. And we observe this with magnets in the refrigerator. You know, stick one piece of paper up there. It sticks pretty good. Keep adding paper, and just a couple extra pieces of paper, and now the magnet doesn't stick anymore. Because you've increased the distance between the magnet and the refrigerator, and that just little increase in distance causes the attraction to fall off significantly. So try to remember that the energy is proportional to Q1, Q2 over R. And then you can reason out a lot of the things that we need to be able to predict. So force of attraction is largest when the objects are close and when the charge magnitudes are greater. So it's important to distinguish between bonding forces and intermolecular forces. Bonding forces are what we talked about in chapters 9 and 10, chemical bonds, overlaps of orbitals, all of that fun stuff. That happens at very close distances. So here's a water molecule. The chemical bond between oxygen and hydrogen involves a separation of about 96 picometers. So these two atoms are very close together. Intermolecular forces operate between the molecules. So the intermolecular forces that hold water together are operating more at 300 picometers. That's 3 times the distance. So you increase the distance of that magnet to the refrigerator by 3 times, and the force of attraction is going to be much weaker, right? It's going to be 3 times as weak. So what are these forces? We're going to talk about 4 of them. So the first one is dispersion forces. We're going to talk about the weakest one first and move up to the strongest. Dispersion forces, this is an intermolecular force that's present in all molecules and atoms. Everything has dispersion forces. It also goes by several other names. London force, London dispersion forces, van der Waals forces, induced dipole forces. That's my favorite, but your book uses dispersion, so that's what I'm going to call them. So what is going on here? Well, here we have an illustration of an atom. What element does this atom belong to? Helium. So we can see there's 2 electrons In the nucleus, we got 4 things, but there's 2 red ones and 2 white ones, so we can assume that 2 are protons and 2 are neutrons. 2 protons, 2 electrons, these are helium atoms. So remember that this electron cloud is like a standing wave where the electrons are. But imagine that we're taking a picture, frame 1, frame 2, frame 3. We're taking pictures of the atom, and we have this magical camera that can actually take a picture of the electrons. When you take a picture of them, you force them to be particles as opposed to waves, and so you can see where they actually are. So you take a picture here, you know, they're kind of on opposite sides. Frame 2, they're really opposite of each other. Frame 3, now they both happen to be on this side of the atom. Can that happen? Sure it can. When that happens, then we have a distribution of charge that's not symmetrical. We've got all the negative charges over here and the positive charges over there. So that makes the atom lopsided. Atoms don't normally have a positive side and a negative side, right? It's a sphere. How could that happen? But if the electrons all happen to be on one side, that could happen. This reminds me of a time when several years ago, when I walked into the living room and all 6 of my children were on half of the couch. They were looking at something on YouTube, or I don't remember what they were doing. I snapped a picture because I knew that wasn't going to last very long. And then poof, it was gone. But these random conglomerations can happen, right? It's also a little bit like taking a blue and white tour of blue and white ferry. No, what's it called? San Francisco. In the bay, there are boats. And you can get on a boat and you can go out and look at Alcatraz. I forget what they're called. It doesn't matter. So you got this boat and it's got a big deck. Because why are you on the boat? Because you want to see things, right? You're not sleeping or anything. You're just going out for an hour or so. So everybody's out on the deck, right? A lot of people. And you get out close to Alcatraz, and what happens? Everybody goes to the side of the boat that's closer to Alcatraz because they're attracted to it. They want to see it, right? So now all the electrons have kind of lopsided on one side of the atom. All the people are on one side of the boat. Is the boat going to tip over? Hopefully not. Hopefully they're following the rules about, maximum capacity and stuff. But you could imagine that the boat might tip just a smidge, right? Just a little bit because all the people are on one side. So that can happen in an atom. It can happen randomly. But when it happens randomly in one atom, then it induces that or causes that to happen in a neighboring atom. So here's one atom that got just randomly lopsided. This next atom over now is a little bit like looking at Alcatraz. The electrons are like, ooh, there's a positive side over there. We're attracted to that. And so these electrons are drawn to this instantaneous lopsidedness of that atom, and now we have a force of attraction. Yes?
So they're not just doing it on their own, it's because they're attracted to another atom?
They're doing it on their own, and they're not doing it on their own. Okay, so one of them will just randomly get lopsided. The electrons will happen to be on one side. That induces a dipole in the neighboring molecule. It is a bit like a domino effect. So normally atoms are symmetrical, the charge is evenly distributed around, but those electrons are moving around and they can both be on one side. And so it happens and then it's gone. So these are instantaneous dipoles. They're very temporary. But this one happens to have its electrons on this side, making this side of the atom positive. An atom nearby sees this positive, partial positive charge, and the electrons in that atom are attracted to it. And that causes the other side of it to be positive, and that can attract the electrons in another one, and that could just go on and on and on. By the time we get over here to this guy being attracted, those electrons are done being lopsided, and it's gone away again. So these forces come and go. They're very small, but they happen frequently, and so they can be pretty significant. Yes?
How does this transfer then physically? Like, to... Like
Well, you can have substances that are only held together by dispersion forces that are liquids at room temperature or even solids at room temperature. So think about Crisco, right? Crisco is solid fat at room temperature, right? The white, greasy stuff. Well, all of the molecules in Crisco are nonpolar. They don't have positive and negative ends. They're not a polar molecule. So they're a lot like this atom. They're nonpolar. But the electrons in those molecules can get lopsided and then induce that in a neighboring molecule. And because those molecules are large, we're going to talk about that in a minute, those forces can actually be pretty significant. And so it holds them together as a solid at room temperature. Then you look at coconut oil. Coconut oil, whether it's a solid at room temperature or not, depends on the temperature of your room, right? We have coconut oil for making popcorn. And in the winter, when the house is cooler, it's a solid, but in the summer, it's a liquid, because the intermolecular forces are not as strong between the coconut oil molecules. And so just a little bit above room temperature or just a slightly warmer temperature and it will melt. That's enough to partially disrupt those intermolecular forces. Does that help? So what affects the size of these forces? Well, it depends on how easily the electrons can be moved around or polarized. How easily can you make this thing lopsided? And so I think of helium as being, it's a small, pretty tight molecule, right? Those electrons are close to the nucleus. And then when I think about xenon, xenon has its valence electrons in what? 1, 2, 3, 4. In the 5th energy level. Those are much farther apart from the nucleus. Xenon is a larger atom in size. Its radius is bigger. So those electrons are farther away, and so I think of xenon as being kind of gelatinous and jello-y, wobbly, right? And so its electrons can be pushed around more easily. They can get lopsided more easily. Does that make sense? Okay, somebody nodded. That's good enough. So as the atoms get bigger, and here we're comparing similar elements, right? These are all noble gases. They all have the same number of valence electrons. And so as the atom gets bigger, well, we see the molar mass increasing, and we see the boiling point also increasing. So xenon boils at a higher temperature than helium, because in order to boil xenon, you have to give it more thermal energy. Now, these boiling points are in kelvins, so all of them are crazy, crazy cold. And this is way, way below zero. And helium is a liquid at, it's 4 degrees above absolute zero. Because the forces that hold helium together are extremely weak. But you can condense it into a liquid. You just have to get those particles really slow so that those very weak dispersion forces can hold them together. It's easier to condense xenon because the electrons are more easily polarized. So when that dipole, instantaneous dipole happens, it induces a dipole in the neighboring atom more easily. And then we get this force of attraction. Does that make sense? So we see that the strength of dispersion forces generally increases with molar mass. So you have to be careful with that comparison, though, because you have to make sure that some other important factors are the same. But looking at atoms, generally, the higher the molar mass, the higher the dispersion force. It also depends on shape. So here we've got N-pentane and neopentane. So N-pentane has 5 carbon atoms strung together in a line. And in neopentane, there's 1 central carbon atom and the other 4 carbon atoms are attached to it. They have the same number of carbons, same number of hydrogens, so their molar masses are identical. But their boiling points are not the same. This molecule has more of a linear shape, kind of looks like a sausage or something, a capsule. This one has more of a spherical shape. So when we think about these two things interacting with each other, this has more surface area to interact with the neighboring molecule. So if you think of these as covered in Velcro, these two are going to stick a lot better than these two spheres will stick, because these can only contact each other really at one point. And so they can stick to each other, but not very well. So this reminds me of those bounce houses with the Velcro wall, and you put on the suit, and you jump and you throw yourself at the wall, right? I've never done that, but I think I should the next time. Just make somebody take a picture of me, because that would be fun. Wouldn't that be fun to see a picture of me stuck to a wall? But you've seen that, right? Or you can imagine. So how does Velcro hold you to a wall when your Velcro shoe keeps coming undone, right? It's like Velcro. How could it be that strong? Well, because there's a lot of it, right? You stick your arms and legs out, and you've got the size of your body to in the suit. You've got a lot of surface area where the Velcro can contact the wall. If you just jumped up and stuck your elbow to the wall, would that hold you up? No. So this is like sticking your elbow to the wall. It's a very weak attraction. This is a much stronger attraction. And so we see that reflected in the boiling points. N-pentane boils at 36, and neopentane boils at 9 degrees Celsius. So this is a much lower boiling point because it takes less thermal energy to break away that just elbow on the wall. It takes a lot more energy to peel these two apart. Any question?
So that's solely based off of molecular shape?
This comparison is based solely on the molecular shape.
They have the same molar mass.
Yeah, they have the same molar mass. And so when we look at molar mass, we would say, oh, well, we would expect their interactions to be the same. But then you also have to consider the shape.
And you can just determine that off the Lewis structure?
Yeah, for this one, you can look at the Lewis structure and see what's going to happen. We're going to keep this, at a very surface level, but this sort of an idea, it also comes into organic chemistry a lot, where you need to predict the boiling points of things, and how branched that carbon chain is going to have an effect. You can have two different molecules, same number of atoms of each element, same formula, but how they're connected is different, and that causes differences in their chemical and physical properties. Here we've got a series of normal alkanes. The N means that it's a straight chain. So this is 5, 6, 7, 8, 9 carbons in a row with hydrogens around. And here we have space-filling models. So the molar mass is increasing, and we see that the boiling point also increases. So not only is this more polarizable just because it's larger, but this also has more surface area that can stick to other molecules than this one does. So both of those are contributing there. Any questions? So that was the dispersion forces. Dipole force. This exists between polar molecules. Everything has dispersion forces. All polar molecules have dipole forces. So here we have a polar molecule. It's got a permanent dipole. This end is partially negative, that end is partially positive. We talked about how we predict which ones are polar and not, and this is where that's going to come in handy. So here we have, again, electrostatic attraction between partial charges, but here the partial charges are always there. They're not coming and going. So it makes sense that this attraction is going to be stronger, because it's like you're permanently going in a circle around Alcatraz, right? Everybody's just going to stay on that side, right? There's nothing interesting on the other side. Why would they leave? So there's this constant attraction between the particles. We can look at the space-filling models. We can look at electrostatic potential maps, or look at how the density of the electrons is. And so they're showing this blue as being deficient in electrons and the red as being extra electrons. And so we have an attraction between the positive and the negative charges here. So all atoms and molecules can have instantaneous dipoles. That's like my kids on the couch, and then it goes away, right? Comes and goes, comes and goes. Polar molecules have permanent dipoles. It's always lopsided. So the polar molecules have dipole-dipole forces, and those are in addition to dispersion forces. So when we're comparing boiling points here, strength of intermolecular forces, we don't want to introduce changes in the dipole force or dispersion forces when we're trying to compare the dipole-dipole forces. So we have two compounds, formaldehyde and ethane. Their molar masses are almost identical. So from that, we can predict that their dispersion forces are very similar. So that takes that out of causing any changes. This is a nonpolar molecule. This is a polar molecule. Okay, looking at this, you should be able to predict that this is polar because you look at the central atom. Remember, in order to be nonpolar, no lone pairs on the central atom and all the atoms bonded to the central atom are the same or have the same electronegativity. We have no lone pairs on the central atom, but oxygen is very definitely different than hydrogen. So this is not symmetrical. This is a polar molecule. The oxygen is going to be partial negative, and the hydrogen end partially positive. Here with ethane, we have carbons and hydrogens. And this is the one bond between different elements that I want you to remember as a nonpolar bond. The difference in electronegativity between carbon and hydrogen is very small. It's only 0.4. So no matter how you put this together, if it's just carbons and hydrogens, it's a nonpolar molecule. So we see a big difference in boiling points and melting points. Boiling point for formaldehyde is minus 19 degrees Celsius. For ethane, it's minus 88 degrees Celsius. Ethane boils at a much lower temperature than formaldehyde. The forces holding the formaldehyde molecules together are much stronger than those holding ethane together. Ethane only has dispersion forces. Formaldehyde has the dispersion forces and the dipole-dipole forces. Any questions? Here we're looking at boiling point as a function of dipole moment. So you can calculate the dipole moment of a polar molecule, or a nonpolar for that matter. And it's measured in debye, and we didn't do any calculations with that, but that's the unit there. And so we see here all of these molecules have very similar molar masses, right? So the dispersion forces between them should be similar. So that's not what's accounting for this difference in boiling point. What's different is that propane is a nonpolar molecule. It has a dipole moment of only 0.08, almost nothing. And acetonitrile is much more significantly polar, 3.92. As the dipole moment increases in strength, the boiling point goes up. Polarity also is important when we think about things mixing together. We did talk a little bit about oil and water and how the water molecules are very attracted to each other, and they basically squeeze out the oil, and that's why oil and water don't mix. Well, what is it that's attracting the water molecules? Well, water is polar, right? So water has dipole-dipole forces. Here we're not looking at oil, we're looking at pentane. C5H12, only carbons and hydrogens. This is nonpolar. It only has dispersion forces. So the water molecules are much more strongly attracted to each other, and they push out the nonpolar molecules. The term we use here is miscibility. We say that the two substances are miscible or immiscible. You need to know what that word means. I won't check your spelling on it. Might help you to think of this as mixability. Okay, that's not an actual word. But mixability, miscibility kind of sound alike. And if I said those are mixable, would you understand what I meant? even though it's not really a word? Yeah, you are able to mix them, right? So if they're miscible, you can mix them together. They mix together very well. If they are immiscible, they are not mixable. They do not mix together. And a little phrase that we have to help ourselves remember this is like dissolves like. So if you have two polar substances, they will probably mix together. Two nonpolar substances, they are alike in their intermolecular forces. They are going to mix together. What if you have polar and nonpolar? They're not going to mix together. Okay? Because they're not alike. Questions?
Are you saying that they won't be separated if they're both polar?
If they're both polar, they will be miscible. They will not be separated. What we have here, this is nonpolar, and this is polar. And so these are not alike. And so they're not going to mix. They're going to form two layers. Okay, so which molecules have dipole-dipole forces? So remember, everything has dispersion forces. What kind of molecules have dipole-dipole forces? Polar molecules. Dipole-dipole, it's attraction between one dipole and another dipole. The dispersion, I have no idea where that name comes from. That's why I prefer the term induced dipoles, because that helps us remember it's dipoles, but they're induced, they're temporary. But your book calls it dispersion forces. So what we need to do is identify if these things are polar or nonpolar. So carbon tetraiodide, we've got carbon, and it's got 4 iodines bonded to it. And if you finish out the Lewis structure, you'll see that all of the iodines have 8 valence electrons. The carbon, does the carbon have any lone pairs? No. Are all of these atoms bonded together? Are all of them the same? Yeah. So we've got no lone pairs and all the atoms are the same. Therefore, this is a nonpolar molecule, right? Do nonpolar molecules have dipole-dipole forces? No. So this is a no for that one. How about CH3Cl? Is that polar? Yeah, this one's different. One of these things is not like the other, right? Did you guys ever watch Sesame Street?
Yeah.
Yeah. One of these things is not like the other. One of these things just doesn't belong, yeah. Oh, memories. So that's a polar molecule. Does it have dipole-dipole forces? Yeah. Well, HCl. These diatomic ones are much easier because you don't really need to do a full-blown Lewis structure or anything. If you have 2 atoms, you have 1 bond. If the bond is polar, the molecule is polar. Is this bond polar?
Yes.
Yeah. It's 2 different elements. I would expect you to say it's polar. The only one I expect you to answer nonpolar is carbon and hydrogen. So this is polar. Does it have dipole-dipole forces? Yes. Anything that's polar has dipole-dipole forces. Any questions? Hydrogen bonding. Okay, this is the 3rd intermolecular force. Hydrogen bonding is kind of a misnomer, and unfortunately the name leads to some confusion. Hydrogen bonds are not chemical bonds. Okay? So hydrogen bonding really is just exaggerated dipole-dipole forces. So it's super dipole-dipole force, with the red cape and the mask and everything. The super dipole-dipole force, stronger than regular. Hydrogen bonding is found in polar molecules that have hydrogen. The hydrogen has to be bonded to fluorine, oxygen, or nitrogen. The reason that it's those 3 is that they are the most electronegative and they're also very small. The smallness is important because the strength of attraction is greater when things can get close together. And because these atoms are small, they can approach each other more closely. The fact that they're most electronegative is important because then the partial charges on those dipoles are larger, and so that also increases the force of attraction. So here we have, well, it doesn't say what that is. It's probably hydrogen fluoride. So a hydrogen and a fluorine. You have a chemical bond between the hydrogen and the fluorine. The hydrogen bond, though, is the attraction between the negative end of one molecule and the positive end of another. It is a dipole-dipole force. It's an electrostatic attraction between dipoles on adjacent molecules. What makes it different is that it's extra strong, like Superman is extra strong, right? So hydrogen bonding is super dipole-dipole force. You need to be able to remember the requirements for hydrogen bonding. You have to have fluorine, oxygen, or nitrogen, and they have to be bonded directly to the hydrogen. If the hydrogen isn't bonded to one of those, maybe there's an oxygen in there, and there's hydrogens, but it's not actually bonded to each other, then it's no hydrogen bonding. Okay? So how do you remember this? Do you remember the movie E.T.? What did E.T. say? He pointed at the sky. He said, "Phone home." Right? E.T. phone home. Phone home. Oh, F-O-N. Phone home. I have no idea why I thought of that one day, but students seem to like it. So you got to have phone, F-O or N, bonded to hydrogen. So here we have hydrogen bonding in water. So here's a water molecule. Is water polar? Yeah, there's two lone pairs on this oxygen. That's what makes it bent and polar. Do we have fluorine, oxygen, or nitrogen bonded to hydrogen? Yeah, we've got hydrogen directly bonded to the oxygen. This is the hydrogen bond. It's the attraction between the molecules. That's the hydrogen bond. This is not a hydrogen bond. That is a covalent bond between hydrogen and oxygen, but it's not a hydrogen bond, which is a form of intermolecular attraction. So here in the space-filling models, it's these dotted lines, the attraction between negative oxygen on one molecule, positive-ish hydrogen on the other. I just made up another word. Positive-ish. It's kind of positive. It's the attraction between those opposite charges. The reason that hydrogen bonding is a separate category is because it is a lot stronger. These charges are larger than in regular dipoles. Here we can see ethanol. So we've got hydrogen directly bonded to an oxygen. It's a polar molecule, therefore there's hydrogen bonding. The hydrogen bonding occurs between the hydrogen on this molecule and the oxygen on the other. It's just electrostatic attraction between opposite charges. Any questions? It's not a chemical bond. Hydrogen bonds are between molecules. Chemical bonds are within a molecule. They are between individual atoms inside a single molecule. Hydrogen bonds are much weaker than a chemical bond. They are the strongest of the intermolecular forces we're talking about here, but they're still much weaker. They're only at most 5% as strong as a covalent bond. So we look at ethanol and dimethyl ether. These guys have the same chemical formula, but the atoms are connected differently. It has the same molar mass. Same molar mass tells us that the dispersion force strength should be roughly the same. This molecule's polar, this one is not. I'm sorry. Scratch that. They are both polar because this has an oxygen in the middle with lone pairs. So they're both polar, so they both have dipole-dipole forces. But this one can have hydrogen bonding because we have hydrogen directly bonded to an oxygen. In this one, there's oxygen and hydrogen, but they're not bonded to each other. So let's look at the skeleton for that. We got the CH3 on one side and the CH3 on the other side. Here's a CH3 and CH3, and there's an oxygen in between. The oxygen's bonded to carbon, is not bonded to hydrogen. There's no hydrogen bonding here. There's dipole-dipole forces, but no hydrogen bonding. Any questions? And we see this big difference in boiling point. Dimethyl ether boils at minus 22 degrees Celsius. Ethanol boils at 78 degrees Celsius. I really wonder sometimes who they get to proofread these books. Group 4A, Group 6A, selenium, tellurium, sulfur, oxygen. What group are those in? They're in Group 6. What?
Graduate students.
I don't know. And carbon, silicon, germanium, tin, Group 4. I got that backwards. So here we're graphing boiling point versus molar mass. And we're looking at these nonmetals bonding with hydrogen. Well, then there's tin that's a metal, but we'll ignore that. We see a general trend for group 4A that as the molar mass increases, the boiling point increases. These are going to be nonpolar molecules because there's not going to be lone pairs. So these have lower boiling points than those in group 6A, which are polar molecules. And we see this trend from sulfur to tellurium. We see this nice, basically a line. What's up with water? If we draw a line here, we predict that water would have a boiling point down here somewhere, right? Close to negative 100 degrees. But its actual boiling point is plus 100 degrees Celsius. That is due to hydrogen bonding. Boiling point is related to strength of intermolecular forces. Water has an extremely high boiling point for its size because of the very strong hydrogen bonding that it has. This makes water a very strange substance, which is good because if it wasn't so weird, we'd not be alive. If it had a predictable boiling point of minus 90 degrees Celsius, all the water on Earth would be in the gas state, including all the water in your body. All the oceans. Yeah, that just wouldn't work for life, would it? So, yeah, we owe our lives to hydrogen bonding, basically. Which has a higher boiling point, HF or HCl? And the dreaded question, why? So we've got HF, we've got HCl. So you're going to see questions like this on an exam where you're asked to predict which is the higher boiling point or the lower boiling point or whatever. And the strategy is you need to identify what types of intermolecular forces do you have. That's going to be the biggest factor. Then if you find out that all the forces are the same, then you're going to look at molar mass, and then you're going to look at shape. So let's list the different types of forces. We've got dispersion. We got dipole-dipole. And we got hydrogen bonding. Do these have dispersion forces? Yes. Everything has dispersion forces. So, check and check. Do they have dipole-dipole forces? Are they polar molecules? Yeah, they're polar molecules, so they both have dipole-dipole forces. Do they have hydrogen bonding? ET phone home. Fluorine, hydrogen, okay? Hydrogen bonding. What about chlorine and hydrogen? Chlorine isn't in phone. Funkel? I don't know. Nope. HF has hydrogen bonding. HCl does not. So this is the strongest intermolecular force. Strong intermolecular force means high boiling point or low boiling point? High boiling point. Those things are really sticky to each other. Lots of Velcro. In order for them to melt or to boil, they need a lot more energy to break away from that stickiness that they have. So HF has a higher boiling point because it has hydrogen bonding, which HCl does not. Stronger intermolecular force, higher boiling point. Yeah?
Why didn't HCl have a hydrogen bond?
It doesn't have hydrogen bonding because in order for hydrogen bonding, you need fluorine, oxygen, or nitrogen directly bonded to hydrogen. It has a bond between hydrogen and chlorine, right? And so that can be confusing. Well, it's got a bond and it's got hydrogen. Yeah, but hydrogen bonding is not covalent bonds. So, ET phone home. Any other questions? Waiting for screen, okay. Ion dipole force. So the first three forces we talked about, intermolecular forces, those are forces that exist within pure substances as well as within mixtures. The ion dipole force can only happen when you have an ionic compound mixed with a polar compound. So you can't get this force within a pure substance. So it's like a stepsister of the others. It doesn't quite belong, and yet it sort of does. This is really important when we have ionic compounds dissolved in aqueous solutions, dissolved in water. This is a stronger type of intermolecular force, even than hydrogen bonding, because what we have here on the ions of the ion dipole is we have a full negative charge, or it could be -2, -3. The charges are larger on the ion than on the dipoles. And so this force of attraction between these oppositely charged things is greater than in the hydrogen bonding. Ion dipole forces are what allow ionic substances to dissolve in water, the force of attraction between the ion and the water molecule. Any questions? Summary from your book of relative strengths. You should know this information. You should know relative strengths. You do not need to know these numbers. They are there for your information, but you don't need to know them. But the names of the forces, what sorts of molecules they're found in, what exactly is going on, how those things are causing an attraction, and the relative strength. So here's hydrogen bonding in your body. Hydrogen bonding is what holds your DNA together. DNA has 2 strands. DNA is composed of a sugar phosphate backbone with these little, what are called bases, hanging off. So cytosine, guanine, thymine, and adenine. Thymine and adenine have a geometry and a structure such that they can engage in 2 hydrogen bonds with each other. So here we have nitrogen bonded to hydrogen. Here we have nitrogen bonded to hydrogen. That's what you need for hydrogen bonding. So this hydrogen will hydrogen bond with a neighboring nitrogen, and this hydrogen bonds with a neighboring oxygen. So that forms 2 hydrogen bonds. Cytosine and guanine can form 3 hydrogen bonds. And so this 2 on 2, 3 on 3 causes these to pair up in the same way all the time. So you've got your 2 strands of DNA, and on one strand you've got cytosine, on the other strand you've got guanine, and they hold together with a triple hydrogen bonding. And here you've got A and T, A on one side, T on the other. They're going to have 2 hydrogen bonds that hold them together. So when your DNA replicates, you've got a little, I think it's a ribosome that comes along and unzips the DNA. And then you've got, or maybe it's the ribosome that brings the new ones. I'm a little rusty on my biochem. You've got these little things that bring in new bases, and it brings in the one that corresponds with what was on the existing strand. So we've separated the 2 strands. Here we have a G, so a C will bond to that. hydrogen bond. There we've got an A, so a T will come in here, and then the sugar phosphate backbone is added. And so it goes along this way remarkably quickly and replicates the DNA. So we have two complementary strands, and when we separate them, we make new complementary strands, and we get two identical pieces of DNA. Very cool. And it's all due to hydrogen bonding. Any questions?